Hello, so today we are going to do this problem, which is part of August daily challenge. So kth smallest element in a sorted matrix. The problem says we have an n by n matrix, and each of the rows and columns is sorted in ascending order, right? And what we want is to return the kth smallest element in the matrix. And by sorted order here, it means not the kth distinct. So we may have equal numbers and we will want to return, let's say, for example, even in this example here, we have two 13s, and the 8th smallest, including this 13 here, is this value, right? We have 3, 6, 7, this one is the 8th, okay? So that's what the problem asks us to do. And here, if k equal to 1, we want the first smallest number, right? And so we are guaranteed that the rows separately and the columns separately are in sorted order. So you can see this row is in sorted order, this one too. And then if you take a look at the columns, we have 1 first, 10, 12, so that's sorted. And then we have as well 5, 11, 13 sorted, and then 9, 13, 15 sorted as well, right? So the columns are sorted separately and the rows. Now, how can we solve this? The easiest way to think about it is, definitely there are like some really easy solutions. You could just create one list out of this entire matrix. So just concatenate each row. So you'd have 1, 5, 9, 10, 11, 13. So you concatenate these, but they won't be in sorted order. So you'll sort the array and then just get the element at position k or k minus 1, right? K minus 1 actually, but that's O of n log n, as where n is the size of the entire matrix. So it's actually O of RC log of RC, right? So it's if the size of the row in the column is n, so n squared, then it's O of n squared log n, actually O of n squared log n squared, right? And so that's not better than O of n squared that we are asked to do here. So that's not good. The other solution is just to take a heap, right? Because a heap allows us to easily get the kth smallest element and just put all of the elements in the heap, right? All of the elements of the matrix, and then at the end just return the kth smallest. And so that would be something like this. So I could just quickly go over it. So it's something like this, right? Where we go through the matrix, each row, each value in the row, push it in the heap, and then return the smallest, right? So this is also O of n squared at least, right? Not counting even getting the smallest element. So that's not better than O of n squared. Yeah, so those are the simplest solutions. So how can we do a better one? Well, it's sorted. The rows are sorted and the columns are sorted. So this hints to use binary search, right? We just need to do it in a clever way. So let's see how we can apply binary search to solve it. Okay, so let's see how we can solve it with binary search. So what we need to find with binary search is a monotonically increasing or decreasing function. What that would mean is basically we need to find a function that has a pattern where once it starts out as false. We have one of two options. So either it starts out as false, and then once that function becomes true, as the mid value increases, it will continue to be true. So this is monotonically, you can say, increasing or whatever. The second option is it starts out as true, and then once it becomes false, it will continue to be false. It won't change. And with our binary search, what we are looking for in this case is either the first true, or the last false, or the last true, or the last false, depending on the function that we want. So we need to think about what function will give us this. And here we are looking for the kth smallest element, right? What does it mean to be the kth smallest element? Well, the kth smallest element means we have k minus 1 elements smaller than it, right? That's what it means by definition, okay? So what this would mean is that with our function, what we can do is actually just find. So what we can do here is actually just find the count of the element smaller than some x. That can be our function, okay? So we can start out with and check if that's bigger or equal to k, right? Because once you have an element, let's say 2, let's say maybe, I don't know, 7 has, and our k is equal to 3, has 3 elements smaller than it in the matrix, then if we increase it to 8, by definition, 8 will have at least 3 elements smaller than it in the matrix. It may have more, but at least that, because 7 has 3 elements smaller than it. If we increase to 9, same thing, right? And so at least we know here it has this pattern. Once it becomes true, it will keep being true. The other aspect is, let's say k is still equal to 3, and maybe 5 has 2 elements smaller than it in the matrix. Then by definition, elements smaller than 5, let's say 4 has at most 2 elements smaller than it. It can't have more, because if that's the case, then 5 has more than 2 elements smaller than it. And same thing with 3, it has at most 2 elements smaller than it. So either 2 or 1 or 0, right? And so this is smaller than our k, right? So that means this is false. So we know also, if it's false, then for the elements smaller than the number for which it's false, it will keep, as we go down, it will keep being false. So with the function count smaller, bigger or equal to k here, we will have this pattern in 1 here, okay? And so we could actually apply binary search with this. Now, are we looking for the first false or the last true? Sorry, for the last false or the first true. So we are looking for the first one that has exactly k elements, that has k elements smaller than it. So we are actually looking for the first true, okay? Okay, so we want the last true. Now, we need an invariant with binary search to not make out of boundary errors. We need some invariants. So with binary search, we'll need to maintain low and high, okay? And in our, this way of doing binary search, we need to maintain an invariant that either low is always true and high is always false, or the reverse. Low is always false and high is always true, right? And so since we are doing this, and low it has to be smaller, we will maintain that low is always false and high always true. So we'll maintain this pattern. So what this would mean is that at the end, we need f to be low to be here and high to be here. That way we can just return high as our solution, okay? And so with this would mean basically if f and true and this is low and this is high, it means with our binary search, high minus low needs to be bigger than 1, okay? So that the gap is just 1. So that's just for the while loop condition. And once it's equal to 1, that means we are at the end, we reached this, okay? Because remember, our invariant is that low, the function f, so this is f of x, is always false, and for high, it's always true, okay? So that's the first thing. So the other consideration is, how do we know where to move low and high? So let's grab this here and figure that out. So let's say our low was here, so it's false, and maybe our high was here. Yeah, these are the mid values, by the way. These are the mid values for these low and high, and this is the f of x function, okay, which is the count smaller than x.
So smaller or equal here, I would say, by the way, because it may have equal values. And okay, so now here, let's say we found that f of x is false, right? Which means basically smaller than k. That means our low, we are here. Our low is here. That means, sorry, our mid is somewhere here in one of the false values. So maybe let's add another false. So what should we do? Should we move it to the, should we move low or right? And where should we move it? So if mid is false, what we are looking for mid is the first true, right? So what this would mean is that we need to advance our low to have a chance of our mid being in a true value, but we'll need to maintain that low is false, right? So if f of x is false, what this would mean is that we need to assign to low the value mid, because we know mid is false, so we maintain the invariant that low is always false. And at the same time, we will advance mid because we advanced low, so that we have a chance of reaching the first true, right? Now, what if f of x is true, which is the case we have, which is the bigger or equal to k? So that means our mid is somewhere here, right? So we want to get the first true. So maybe our mid is the first true, and we don't know, right? And so to maintain that, we need to just make our high be at the value mid. We will maintain the invariant that high is always true. And at the same time, we'll have a chance because we will push high to mid to reach the first true, right? Where the difference between low and high would be just 1, right? So this would mean our high would be equal to mid. Okay. And what's good in this pattern is that you don't need to think about, okay, should we do mid plus 1? Should we do for low? Should we do for high mid plus 1? Or the reverse, should we do mid minus 1? This makes it really easy. Each of them would be equal to mid with this pattern. And also with knowing the invariant that low is always false and high is always true, that will help us pick the boundaries. Basically, what should be the initial low and what should be the initial high. So let's think about that. So we know low needs to always be false. How do we make it false? We want the kth smallest element. So to ensure low is false, regardless of k, let's just make it not even in the matrix, right? That way we will guarantee it's false. So we can just pick the smallest element in the array, in the matrix, which is the element at 0, 0, minus 1. That way we guarantee that, so this is the initial values. That way we guarantee that this invariant of always false is valid. Now what about our high? We want high to be true, so we want the smallest, bigger or equal to k smaller number. So we can guarantee that by just picking an element outside of the matrix, because that would be the greater than all of them, so it would have this condition valid. And so because we want to keep this invariant, and we want the search space to be in the matrix, right? And so we could pick this to be the last element, which is the highest, and just add 1, right? So with this invariant, that also helps us pick the initial values, okay? And now I think we have everything to do our binary main binary search. We know what will be our while loop condition. We know the invariants we are going with. We know when the function is true, what should we do? And when it's false, what should we do, right? So the only remaining thing is how do we calculate the smaller than or equal x in an efficient way. Let's see that. Let's see how to. Okay, so now how do we find the count for the element smaller or equal than x? The easiest way to do this is actually to utilize the fact that rows are sorted and columns are sorted. So what we can do is, we know the bigger element in the row is the last one, right? So we can start from the last one for the first row. Okay, let's say our x is equal to 8. We want to know if it has and k equal to 3. We want to know if it has. We want to know how many elements are smaller than 8. Okay. So we start with 9. We check if 9 is So we check if the element at that row and column, so we start with row equal to 0 and column equal to the last one, which is 0, 1, 2, which is 2. So we check if that element is smaller or equal to k, to x, which is 8. Is it smaller or equal to 8? No, this is false. So what should we do? So it's bigger. That means if we go left, we would have a chance of finding smaller elements, right? So if we move our pointer here, we'll have a chance of finding elements smaller than or equal to 8. So what does this mean basically is doing column minus 1. Now 5 is smaller or equal to 8. So what can we deduct? How many elements are smaller than 8 in this case, are smaller than x in this case? Well, since this is the larger element than all of those to the left of it, we know that how many are to the left of 5, including 5, are smaller than 8, right? So we can just increase the overall count of the elements smaller or equal to x by everything to the left, including the element. And this is column, so, and this here equal to 1. And we know it's 2, so it's column plus 1, right? It's everything here is the value column, and this is because we are starting an index from 0, so we can just add column plus 1 to our count. Okay, so all of these to the here, if we have something like 2, 3, 4, 5, 9, so the indices are 0, 1, 2, 3, 4, 5, right? So all those small, it's everything here, and this column 4, because the index is 0, these are 5 elements, right? And so this is column, so it's column plus 1. That's why we add column plus 1. Okay, so that's the first thing. Now, what if it's so now once we find 5, we want to find how many other elements are smaller. So we go to the next row, right? So we check 11. Is 11 smaller or equal to 8? No. So we go to 10. Is 10 we go to column minus 1. Is 10 smaller or equal to 8? No. So we go to minus 1, right? And now minus 1 is not a valid column anymore. So our while loop that keeps doing this needs to have the condition that column bigger or equal to 0. The other thing is that once we are done with a row and counted it, the element smaller than or equal to k, you saw what I did here, which is go to the next row, right? So basically what this would mean is if the element at row column is smaller or equal to x, what did we do? We increase the count, right? So we increase the count, but we also go to the next row because we already counted how many smaller are in this row, so we go to the next row. But if it's bigger, right, which is what I did here when we were at 9, we saw that it's bigger, and we know that to find elements smaller, we need to go to the left. So we decrease the column. So otherwise, we decrease column. Okay? Now, one thing you would say, okay, if we decrease column and end up going 11 to the bottom, is that right? Like, could 13 be smaller than x? It can't, because by definition, columns are sorted. So if 9 is bigger than x, then by definition 13 is bigger than x. So decreasing column minus 1 is the correct thing to do, because we will never find an element smaller or equal than x in this column, right? So that's the main idea here. We can just do a while loop and decide to go left or right, depending on the values we have. Okay? Yeah, I think that's pretty much it. So now we know how to calculate the count smaller than or equal, and we know how to do our binary search, so let's just code this solution. Okay, so let's write the function that we just saw in the overview. So we know that we need to do binary search first, right? So we need the values of the number of rows. I'll just make this m to make this easier to write. And m of 0, right? And now we need our low and high, and as we said, we want low to maintain the invariant to always be false. So to ensure that, we will pick the smallest element in the matrix and do -1, and no matter what's the k value, this will make our function on low be false, which is how many elements smaller than or equal to x, the count of the number smaller or equal to the value is bigger or equal to k. And then for high, we need to go outside the bound to guarantee that we have it true. So we would go to take the higher element in the matrix. So this can be r minus 1, c minus 1, which is just this in Python, plus 1 for high. So we maintain the invariant. Low, the function is always false. For high, it's always true. And for our binary search, our while loop, we want to maintain as long as the gap is bigger than 1, which means we are not at what we said in the overview, which is we are not at. So we are done when low is here and high is here. So the gap is just 1. Okay, so that's why we continue as long as the gap is bigger than 1. And now we calculate our mid. And the way to calculate it, to avoid overflow, is just do low plus high divided by 2. So we can do that with this shift 1. And now we check if our function, which is count smaller or equal than, for mid, if that's bigger or equal to k, right, which means this is true, so we are in some of the true values, we need our mid to be just, we need our high to be just equal to that, because maybe we are here, and so we want high to be equal to mid. And for the else, which means that our function is false, so we want to maintain that low is at false. So but we want to get closer to the last false. So we set low to mid. So we do that, set low to mid. Okay. And then at the end, we want to return the first true, which is high, right? Because the gap is just 1, that means the first true is this high value here. So we return high. Okay. And now we need to define this function. And we just get a target value. And as we said, we will initialize row pointer and column pointers. Row will start with the first row and column with the end of the first row. And so that would be column minus 1, the number of columns minus 1, right? And we want a count that counts the overall number that we will return at the end. And we will keep searching while row is not past the last one, so we haven't explored all the rows. So smaller than number of rows that we have here. And column is positive, right? If we go past the first element in the row, so the first column, then we are done, right? And now we will check if error, so this is R actually, RC is smaller or equal to target, right? That means we found the first element in the row going from the right that is smaller than our x. So let's actually call this x. That is smaller or equal to our x. So we need to count. And it's everything to the left of that, including the element. And so we increment by column plus 1 because we start the index from 0 in the row. And then we advance to the next row to check if we find anything smaller or equal to x. Otherwise, it's bigger than x, right? So there is no chance to find anything smaller than it in the same column. So we just decrease the column. And we leave the row because we want to still see if we find something smaller or equal than x. And that's pretty much it. So we can run this. So this is actually C, and this is R. And this is C as well, sorry. Okay, and let's submit. Okay, and that passes test cases. Now this is, the function here is O of n log n, and that's just the overall matrix, right? So O of log n, sorry, O of log n squared, that's the size of the matrix. And then, since it's a square matrix, and then here, this we will do at most, I think, we'll do, I think, at most k, right? So yeah, it's definitely faster than O of n squared. Yeah, so I think that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.